name is Adrian Chong, Assistant Professor from the Department of the Built Environment at the College of Design and Engineering in the National University of Singapore. I'm very glad to be invited to share with you, our work in this presentation titled The Total Building Performance Approach to Real-Time Occupant-Centric Sensing and Control for Mixed-Mode Ventilation in the Tropics. So before that, let me give an introduction of my lab. So my lab is known as the IDEAS Lab, which is the acronym for Integrated Data, Energy Analysis, and Simulation. So we work a lot in working with real-time data and integrating that with building energy modeling and simulation. And so if you're interested, feel free to scan the QR code and then check out my group's work. So recently, just to give some background as to why we get into mixed mode ventilation is mainly because cooling consumes, substantial energy in Singapore, given that we have a tropical climate, so a hot and humid climate. And therefore, right, mixed mode ventilation provides significant, a potential for lots of energy savings, as can be seen from this graph that I show. So however, previous attempts at mixed mode ventilation were not successful. And these spaces were often, converted into air-conditioned space to meet comfort requirements. So this is also in line with, recent publications that we've seen that states that, a tropical climate has little, to no potential in natural ventilation. Additionally, right, previous attempts in mixed mode ventilation also do not consider noise and air quality. And therefore, this is where our research comes in. We felt that recent advancement in technologies has brought about opportunities that could lead to effective mixed mode ventilation. So this includes the hybrid system. So just to give some background, the hybrid system has become increasingly used in Singapore. So what the hybrid system is basically we provide elevated temperature to save energy to reduce our demand. So instead of a set point of a typical 23 or 24 in the tropics, we are having a 27 or 26 or 27 degrees Celsius. And how we still achieve comfort is to have elevated air movement through ceiling fans. And additionally, right, besides that, technology has also advanced. There is a lot of advancement in real-time sensing, occupant feedback, and controls. And there is also advancement in simulation and machine learning, whereby we can optimize the building systems through modeling and simulation in real time. So this is what we hope to achieve: real-time occupant-centric sensing, as well as mixed mode ventilation in the tropics. So if you look at the figure on the left, the things that we target, we try to achieve, thermal comfort, indoor air quality, as well as acoustics. And how we aim to achieve this is through elevated air movement. We have an operable plenum window. So in the plenum, what we line is we line it with acoustic absorbers, with the aim that when it's noisy outside, we will open in a semi-open mode, and that reduces the traffic noise or like the outdoor noise. Smart controls. So we'll be looking at some of the smart controls technique that we implement in a test bed that you see on the right. So the test bed has already been recently completed, and I'll share a little more about that. So occupant-centric in two ways. One is that, for our smart controls, we will be predicting occupancy. And the other thing is, we'll be getting their feedback through wearables. So I'll also talk more about that later on. And modeling and simulation is something that we use throughout the entire, from the design phase all the way to operation of the test bed. So our proposed approach basically is that we want to minimize the overall energy consumption while maintaining thermal comfort, acoustics, as well as indoor air quality. And real-time sensing and controls, as well as real-time occupant feedback, are central to our smart control strategy. And how we aim to do this is not to suddenly operate in natural ventilation, but rather we might operate in air conditioning. And if we see that the outdoor conditions are going to be good, we will move to a concurrent operation. So concurrent is basically we are operating the air conditioning system as well as having the windows slowly open up as we increase, the thermal load into the space. And then we switch to natural ventilation so that there is not too much sudden changes in the temperature or how the occupants feel, and vice versa. So when we move from natural ventilation to air conditioning, it's the same approach. And if you look at on the bottom right, we also have a desk supply system installed in the test bed. So during concurrent operation, what we think is that instead of cooling from your ceiling diffusers, we'll be supplying from the desk. So it's kind of like a spot cooling to provide further comfort and providing occupants with control of the systems. So I'll now move on to the smart controls that we are currently investigating. So just to give some background, if we were to look at rule-based control based on outdoor temperature, so this is typically what people recommend, what is recommended in the literature when it comes to mixed mode. In Singapore, given Singapore's climate, if we were to open windows only when outdoor temperatures are less than 29 degrees Celsius, our window opening, our opportunity to operate in natural ventilation is probably like around 10%. So that's not very much. And from our literature, from a recent lit review, what we found is that almost 50% of the studies that consider outdoor temperature also considered indoor air temperature. However, dynamic window opening and dynamic room set point is seldom considered. So it's often at a fixed set point, like when the outdoors are 29, open the window. So based on this, we started first exploring. Since the rule-based control doesn't work very well, we were thinking, how about learning-based solutions? So we applied reinforcement learning on a virtual test bed of a virtual model of our test bed. And basically what we explored is what we feel window opening that goes from 0, 25, 50, 75, and 100%, and a cooling set point between 24 and 27 degrees at 1 degree Celsius step. And we found that, we were able to reduce our cooling energy by more than 50%. So that was very surprising. And we were thinking, what exactly has happened, because ultimately this is a black box solution, reinforcement learning algorithm. So what we did was that, we extracted rules. So we use, we applied decision tree to the RL algorithm, and we managed to see, try to understand exactly what exactly is happening in this test bed. And basically what we found was that, the reinforcement learning algorithm was taking advantage of the internal thermal initial to increase cooling efficiency. So what was happening was that, if you look at all this gray bars, these are basically when it is operating in air conditioning mode. And when there are no gray bars, it is when it is operating in natural ventilation. And during natural ventilation, what we were using was the adaptive thermal comfort model. So it generally it is a thermal comfort models that adapts itself with the outdoor conditions. And as you can see here, what happens was that, the windows were opening and closing. So it cools to 24 degrees Celsius when it's not too hot outside. And then it opens up with a smaller window opening to take advantage of the thermal initial and the smaller load, and so that we can operate in natural ventilation for a longer time. And then it closes back and then it cools again. And when it's really hot, it opens up for a shorter period of time because the outside load is a lot higher. So this was pretty interesting because it shows the importance of passive design for achieving effective mixed mode ventilation, as I think Ian has also pointed out in his presentation. So what's next? So right now I'm working with one of my colleagues, Dr. Clayton Miller, on wearables. And in fact, right now the experiments are running. The test bed was just recently completed in June, and we want to, confirm and validate, what we have found through our virtual model in the actual test bed. So what you see here is, on the left is the image of the test bed, and on in the middle, right, we have image of the wearable technology. So basically what's going to happen in our experiment next week, in fact, is that we're going to ask occupants, how do you prefer the temperature and air movement? And we're going to use that to optimize the test bed, energy consumption and the comfort while maintaining comfort. And on the right here, you'll see this is basically our building management system. So IoT is key to all this. So the building management system is right now set up such that we have a web API that we can write a Python code or R code that sends a signal write access to the test bed after accounting for all the data that is being collected in our test bed. So I'll move on now to occupancy. So occupancy is also key to control strategies. We have previously found strong positive correlation between Wi-Fi, which is a proxy to occupancy, and energy consumption across 4 different building types. And therefore, right, however, one issue is that being able to directly sense the number of occupants in a space can be costly. And this is particularly important in Singapore, where fresh air provision can be very expensive, can significantly increase the cooling load because our high humidity levels outdoors. So to address this, what we've done is that we have created a roof level occupancy and building operation data set. So it's a very extensive data set, but I won't go into the details of that. And what we have done is that we have applied transfer learning. We were trying to look at, whether, when occupancy data is limited, because that is very expensive, can we, use a different data set that with lots of features and lots of data, so information rich building to kind of predict occupancy in a building with sparse information. And our study so far, we've looked at within Singapore from the same building and across different buildings. So there was a recent ASHRAE Global Building Occupant Behavior dataset that has recently been published. We took 2 of those buildings and we tested whether we can, apply transfer learning and see how that affects our predictions in Singapore. And generally, it's seen preliminary results show that there's a positive transfer. So that means that it is increasing our predictive accuracy. So the other aspects that we have looked at is also, we were concerned about noise on comfort. And we found that, this is an experiment that we run. Above 50 dBA, thermal and acoustic comfort are not independent of one another. So above 50 decibels is actually, affecting how we feel thermally. So this is still work in progress. What's next is that, so far in all our simulations and experiments, we've been looking at adaptive thermal comfort in a mixed mode using the adaptive thermal comfort model that is proposed in ASHRAE Standard 55. In the next, what we're going to do is we want to understand exactly how occupants feel. So we are currently, planning. In fact, this experiment was just completed last week. We carried out an experiment with 60 participants where we have the same participants exposed to natural ventilation, air conditioning, and concurrent operation under varying temperature set points and ceiling fan speed. So this is stay tuned to this. If you check my lab website, I'll probably post something about it in the next month or 2. So to kind of summarize this project, we have been, as the research team, right, we have been involved from the concept design to the detailed design to the construction. We were just doing the testing and commissioning last week, and right now it is operating with all our, experiments ongoing. And throughout all this, one of the important things that we've been doing is that we've been using energy simulation to inform decision and quantify our mixed mode potential, like you have seen with the reinforcement learning that I showed earlier. But one of the things that we noticed is that there was significant information change as we move from one phase of the design to the next, all the way to testing and commissioning. And what we were thinking is that, we want to be able to identify these changes, as the whole point is that we want to understand, how does this affect the decisions that we made at the start, and if we made those decisions differently, would it affect how we would have operated our buildings? So this is towards more robust simulation, so that the next time when we were to simulate mixed mode ventilation or try to design mixed mode ventilation using simulation, we would then be able to know which are the parameters that we need to maybe introduce some uncertainties and model them. So this is how it all comes together. We are right now, it's exciting time for the team. Everything we are trying to put all this, you realize that we are running in parallel, and we want to put this into a scalable and effective mixed mode control framework. And right now we are working on the validation. So if any of you ever come to Singapore, feel free to reach out. I'll be glad to show you around the test bed. So besides the mixed mode, I also want to quickly introduce two work that my lab does. One is data-centric performance evaluation or model predictive control. So this is where we look at various occupant-related data and try to investigate their effect on control performance. And the other one I thought was related to this workshop was we've been looking at in energy flexibility. So we were using MPC, model predictive control, to regulate the room set point temperature so that it aligns with building load generation by photovoltaics. And we found that PV self-consumption and building self-sufficient can be improved by close to 20 and 10% respectively, just by shifting the temperature set point across the day. And with that, I end my presentation. Thank you very much.